persevere through difficult questions.
Taking as long as possible to look at the mark scheme is the thing that helped me improve the most.
Just keeping on working until you really understand it, as opposed to just have done it.
It's the same skills, just do hard questions, talk about hard questions.
And I got a gold medal.
Also won a gold medal. These
5th in the world. The algebra will get harder than this, I promise.
You look at any space mission and it probably boils down to a series of these with.
Okay. And finally, I'm just going to sub in MT, which, as we got up there, is half km, which is cool because you never really see like such high powers in a lot of physics.
We have this expression and it looks quite horrendous.
It's going to get worse than that. And then we've got another binomial expansion to do. Yay! So I'm Charlotte. I am currently going into my 3rd year at Oxford. I'm doing physics and philosophy, which I love. I was on the team in 2023 with Ben and then 4 other guys. And I got a gold medal at the astrophysics Olympiad.
I was also on the 2023 team in Poland, also won a gold medal. And these
5th in the world.
Yeah. And
wow.
yeah. And these days I just finished 2nd year maths at Oxford, and also along with Charlotte, one of the UK team leaders for the IOAA team going to Mumbai.
So what's the secret to getting a gold medal? What advice would you give to anyone who would like to be in your position?
It's just problem-solving skill. I mean, whether it's maths or physics or astrophysics or anything else, it's the same skills. Just do hard questions, talk about hard questions. There's so much to be gained from talking to someone else who's also had a go at the question and maybe thought about it in a different way. Because with these sorts of difficult questions, there are so many ways of doing them, and the different ways of doing it are going to be better or worse for some questions. So the more perspectives you can get on these different approaches to questions, just the bigger toolbox you have when someone throws something new and horrible at you.
Yeah, I completely agree. I think one of the most amazing things about the UK training process that we have, so once you get on the team, we go through like 4 months of just like a lot of looking at Wikipedia articles, having no idea what's going on, and then doing like a bunch of practice questions. But the whole time you're very much connected to the other people on your team. And there's always, you know, team leaders, but also other team members who are there to sort of contact at any time if you need help. And it generates like a really lovely community vibe, which really helped me just to sort of be so open with things I was struggling with. I think that's a really unique thing. One thing I'll say is there's a lot of problem solving in IOAA. There's also a lot of memorization. And for that, just like start early. This goes for not necessarily National Olympiad too, but we have some sort of observational components. Basically just like, don't see it as, oh, I have to learn all these stars in one night. See it as maybe, you know, you learn 10 new ones a day. Quizlet's good for that. I really loved Anki. But basically just start early, take it easy, just like be prepared for the memorization aspects.
But also learning these things, I mean, it feels like a lot of tedious rote memorization at the time, which it is. But once you know it, it's just brilliant to be able to go out under the night sky and know all the thing. It's you gain a new appreciation for this, and you know, if you get an opportunity to look at it all through a telescope and stuff, it's just wonderful.
Yeah, completely. Like not even just knowing the constellations, but like we have to learn the Messier objects and some other deep sky objects, and just like being able to look at some random dark place in the sky and be like, oh, there's, you know, a globular cluster there, there's, you know, a supernova remnant. It's so cool. Even if you can't see it, just like knowing that out there somewhere is amazing. I think it's an amazing skill to have.
And when did you guys start your journey with the physics and astronomy Olympiads? So was it in sort of year 12 in school? Was it a bit earlier? What was it like?
So I didn't really know they existed, but I went to a math school, which meant that there was a lot of sort of Olympiad stuff going on and a lot of people took part in it. I was really lucky to have that experience, which meant that we were sort of just entered for a lot of things. So I did BAAO Round 1 because it was more well known, and I wanted to do physics at uni, so I thought it was a good idea to sort of just get something down so that hopefully if I did well I could talk about it on my personal statement. I then got through to round 2. I didn't actually do physics round 2, but I did astro round 2, and that went okay, I guess. But before that, I hadn't really done much astro at all, really. I had a teacher who was really passionate about it, so he'd do sort of lunchtime classes sometimes where he'd talk a little bit about astro, but beyond that, I didn't really have any exposure. But I think it's quite good, the Olympiad. It's sort of, if you haven't really looked at it before, it's quite easy to break into, even if you don't have that specialist knowledge.
Yeah, I mean, I similarly qualified for the astro via the physics route, as most people do. I mean, we're trying to get more people taking the astro round one, and it's slowly getting there. But at the moment, most people are coming to it via the physics. And
For anyone who wants to take it, I think next year's round one is around January time.
round one next year, it's been brought forward a bit, so it's in December.
It's in December.
It's more similar to physics round one.
And the best thing, I guess, would be for them to ask their teacher to take part in the Olympiad.
Yes, absolutely.
Just annoy them as much as possible. It's quite easy to sign up for the teachers, so they have no excuse.
Could you guys give any tips for anyone who is interested in applying to Oxford and Cambridge? So you guys would have obviously done incredibly well with the entrance exams. Any sort of tips that you might want to give to anyone watching?
I think, obviously, a lot of people say, read loads of books, have loads of stuff on your CV, personal statement. I didn't really read too many sort of specialist physics books beyond sort of, the Stephen Hawking stuff, which is amazing to read, really enjoyable.
But yeah, just for the viewers, like we're currently in the building where Stephen Hawking actually used to work. His office is around here somewhere. I'll see if I can get a selfie later.
But yeah, beyond that, I'd say it's not super important to have all those books that you can just list off. I think just the ability to find an actual physics concept and just burrow into that and do practice problems on it. Find some hard problems, ask your teachers about them, and then you just have sort of a journey to talk about of, oh, I found this concept, I really liked it. It's not in my spec, but I sort of just dug into it a little bit and asked my teacher about it. So you don't need to do straightforward reading one book. It doesn't need to be really regimented, documented research. It can just be you went down a few Wikipedia articles and found some really interesting problems and got stuck on them. Beyond that, for the application tests, just practice a lot. It's really annoying because the PAT recently changed format, so there's not really much practice stuff you can find online. I'd recommend, if you want to practice that kind of format, the Cambridge Engineering Assessment papers are really good for that. It's just a lot of quick fire physics problems, and it's very similar syllabus, although I double checked that.
Do you think doing the BAAO rounds was probably good practice as well, just in general problems, even with the format?
Yeah, I mean, no matter what the format is, you need to just solve problems quickly, and BAAO is amazing for that. So I definitely recommend definitely doing them in your year, but also if you've run out of PAT preparation stuff, sort of from the website, then BAAO has an amazing bank of questions that are really well thought through and really interesting. Yeah.
And you did the math?
Yes, I did, yeah.
You joined the dark side with maths?
I didn't join it, I was always there. But yeah, it's exactly the same problem-solving skills, whether it's the MAT or the PAT or whatever the Cambridge ones are, or the Olympiad things. It's those same, being able to look at a hard problem. Because A-levels, basically every A-level problem, you've probably seen some permutation of before. Whereas these admissions exams and the Olympiad exams and the interview questions, you probably haven't. And it's going to be something you know how to do. You just have to find it. And there's a knack to that. And it just takes practice. And I think especially for the interviews, it really goes back to what I was saying before about talking to people about hard problems in your subject. You need to be able to talk about your subject, because there's no point knowing the answers if you can't articulate them.
Yeah, I mean, even if it's just rehearsing, going through interview questions to a mug or a little plush toy, it's better than nothing. Like Ben said, I think the art of not waffling, but being able to sort of hit the ground running and start vocalizing your thoughts immediately, even if you don't necessarily have a full plan of how to do a question yet, is it doesn't come naturally to me, at least. So I had to really sit down for a few hours and work out how to start a question and how to sort of talk through my thoughts, even if I didn't really have many thoughts at that point.
Yeah, they don't want to know the answer, they want to know how you think.
Yeah.
And that's in many ways, it's very true for the interview, but I think it applies to the admissions exams and the Olympiads as well. Write down some ideas and there might be marks for that, depending on the format of the exams. But
Yeah, they don't want you to just solve the problems, they want to get you stuck and help you out of that hole and see that you can respond to what they're saying. They're trying to simulate a tutorial, which obviously you're not going to be, unless you're like crazy, like, but no one is really. Everyone gets stuck at some point in their degree. And they want to make sure that they can help you if you get stuck. That's really what interviews are about.
Thank you so much. And you guys also do problems as well, as in you create problems and you're part of this wonderful community with the Astro Olympiads. What's creating problems like?
it's a lot of fun because it's those moments where you just want to, I wonder how that works. And then it's an excuse to research it and solve it and present this solution in this really unique way and then share it. And I always find that a good Olympiad problem boils down to, you can summarize it in one question, like, you know, how much fuel does it take to send a rocket to Mars? And then it turns out that that one question branches off into all these other little questions that you need to answer to be able to answer the big question. And it's really satisfying trying to piece that together in a way that you can present to someone else and they can work through it in a way that, you know, if you just presented them with the original question, they might not have even known where to start. But if you write it in the right way, you can get someone to solve something genuinely interesting.
That's amazing.
Yeah, I mean, so the question I wrote that I go through on the board, I found quite daunting to write because it's quite a long question. It's supposed to take an hour, and it's like I had to sit down and be like, okay, what do I have to ask? Like, you know, lots of people from across the country to spend an hour of their lives on. Like, it's kind of crazy that you're reaching that many people with it. And I think the topic I chose was it got very complex very quickly, and a lot of algebra that's a lot worse than that, if you believe it. So I spent a lot of hours, probably comparable to the amount I spent actually writing the question, sifting through research papers and trying to get back to ones which sort of reach the core of the theory instead of, you know, all the later ornamental stuff of like, oh, what happens if we change this parameter, or like the basic theory of it. I ended up going back to about the 60s in my research. So some of this question is based on papers from, you know, 60 years ago. It took a long time, but I learned so much from it. It's really challenging, I find, at least in the topic I chose, to sort of cut down all the really complicated stuff and get to something which is not physically inaccurate in that you're making crazy assumptions which just like make your head hurt in like how wrong they are, but also like don't make your head hurt in how complicated it is, and actually you have some intuition as to what's going on, but you're not like misdirected by the assumptions into something, an incorrect belief. But I really enjoy the process and I love marking. I think I really like seeing how people think, and it's so lovely to see like people answering my question and putting so much time into like something that I put together. I really enjoyed marking. I think that's my favourite part.
I'm Dougie. I was on the 2024 IOAA team. I got gold in Brazil, and I'm now doing maths at uni.
I'm Arzaf. I do physics at Oxford. I've just completed my first year and I got silver in Brazil.
I'm Nola. I'm also doing physics at Oxford, and I also got silver in Brazil last year.
What was the secret? How do you get so good at problem solving?
Practice. I think just the best thing you can do is problems which are like a little bit harder than what you can do, because that's the only way you're going to improve, is by doing stuff you can't do, sitting with it, really trying, getting to the point where maybe you do get stuck, trying to go for little hints rather than just looking at the complete solution, and just keeping on working until you really understand it, as opposed to just have done it.
At what point did you start preparing for Olympiads out of curiosity, was it in year 12 or did you do any of the GCSE ones?
I didn't do the GCSE ones. I prepared for the physics challenge in year 12, so I'd been doing that, and then obviously preparing for the physics Olympiad in year 13. So I'd sort of, I think, started around sort of end of year 12. In terms of astro, I didn't really know about it until I got invited to round 2, but that shows that actually a lot of your physics skills are really, really transferable for astro, unsurprisingly.
Yeah.
So at what point did you start preparing?
I did do the year 11 and year 12 ones, but they were quite shocking. So I guess I did prepare for those ones, but I like really started during the entrance test times. So like preparing for the PAT kind of got me into the mindset for problem solving, and I just kind of kept going for the BPHO.
Amazing. I guess there's a big overlap between the two in terms of just preparing for hard
Yeah,
exams.
yeah. Like it's a thing that if you prepare for Olympiads, usually just like happen to do a lot better for harder exams because you just kind of knock down on marks even for impossible questions. Like you get into this mindset that you can kind of just like work and persevere through difficult questions and knock down on a couple of marks, even if it means you end up getting like 35%, which is fine because that's probably close to the average. But yeah.
Yeah, I started doing Olympiads basically when I finished all the PAT papers and I was looking for more things to do. I was like, oh, I don't know what to turn to. So I found the Olympiad papers, I started doing them, and then that actually exposed me to the fact that I could do the physics Olympiad. And then I just carried on doing the papers and then sat it in whenever it was, November. And then, yeah, got into round 2. And then that was when I found out about Astro as well. And I started like looking into the spec a bit more. And then, yeah, that was it basically.
So when you're preparing, how much of the mark schemes are you actually looking at? Or at one point do you decide, oh, like this problem, I'm hopeless on this problem, I'm going to have a look at the mark scheme?
Yeah, I think taking as long as possible to look at the mark scheme is the thing that helped me improve the most, because the thing that's different about Olympiads and the PAT and things like that to A-levels is that you have to think for yourself. Like in A-levels, they kind of guide you through every question with different parts and they say, okay, explicitly calculate this. But in Olympiads and university especially, everything is kind of by yourself. They'll give you an end goal and you have to figure out the steps between it. So training yourself to find the route to the end is, I think, something that really is very different to A-levels, and that's what needs to be practiced. So if you look at the mark scheme, you're giving yourself the steps and part of the route, even if you're just looking for like one part of it. And that takes away, I think, a little bit from kind of the skills that you need to develop to do well in the Olympiads. So I just took as long as possible.
I bet that's really helpful for the university as well.
Yeah, absolutely.
There are some questions in which you can look at the answer and you can stare at the mark scheme and still not get how the question is done for hours. Happens all the time for IOAA questions as well. So usually, going back to the question, just spending maybe one more hour just like wrapping your head around the question and maybe solving it in a different way to the mark scheme can actually like help you learn a lot better.
Definitely. There's no better way of like learning how to do questions than doing them. And like really sort of it was certainly my rule that there has to be something written down on your paper before you're looking at a mark scheme. And as far as possible, it should be you're using to check something you've had a go at, rather than like hints are good, but even better if you can try and sort of have had a go, even if it's completely wrong, because you've just been engaging with it and thinking about it, and that's the key.
I think the astrophysics and astronomy Olympiad is quite unique because you are also developing huge observational component that I ended up having to do in the middle of the night. And you're looking at the night sky and you have so many conditions to work with. How did you guys find developing that side of the Olympiad preparation as well?
I mean, it's really different. So I really enjoyed it because it was sort of, I felt it was quite easy to sort of energize myself learning it because it was a break from some of the, the conventional physics side of it. I started by just sort of getting some stars down. Just, I knew them, they were the bright ones, try and find them, and then they work as pointer stars. And the way the astrophysics Olympiad works is there's not many you need to know for Astro Round 1. So that gets you your sort of basis. And then as you're slowly learning more stars, and we did it by constellation generally, but as you're slowly learning more stars and more constellations, doing as much practice actually on a night sky, and just going out and looking and just enjoying your new knowledge, because it's a great way of cementing it, but also sort of just having a think about what you have learned. And that was useful for keeping me going, I think. Star maps, there's lots of websites you can get star maps from, and they were useful. But the fun of doing it on an actual night sky, especially with my family, they got tired of hearing all the star names.
Oh, that's amazing.
Revising obs is definitely a lot easier, a lot more fun, because it's just pure memorization, essentially. I guess just look at stellarium and star maps and keep reading them until they're ingrained in your head.
Yeah, that's literally it. You just have to keep practicing, like putting stars on the map and then just rubbing them off again and trying again until you get all of them, until you fill in patches of the sky. And then eventually you can kind of piece them together to make the whole night sky. But yeah, it's just practice.
What's the best part?
I mean, I just love mechanics, basically. The celestial mechanics is really, really interesting, I think, because in this part of the Olympiad, you're introduced to a lot of new formulae that are actually incredibly useful for uni mechanics, I've found as well. And it's just very, very neat, and it gives you a new perspective on how things actually move in orbits and sort of really nice methods that you can use to solve them.
I like the DA because a lot of it was just like writing numbers from a calculator.
Data analysis, I might.
That's it, yeah. And it's very statsy. Yeah, I wanna go into quant. Proudly sponsored by G Research. Please hire me.
I quite liked the sort of colours and magnitudes and photometry and that sort of stuff. When we got into the later part of the training, the radio astronomy, that sort of thing of like observing stars, because it's a bit different to what you'd usually might do in A-level physics. It's quite different, although they touched on it in the Astro module, and I found that lots of fun. Although special relativity, kind of, when I learned it for Astro, it was just a bit scary, but now I've done it at uni, it was actually lots of fun. So I'm enjoying the students doing it this year.
Right, Charlie, you've done some problems as well.
Yes, I have.
Right, let's have a look. I'm really, really curious. So what Olympiad was that for?
So this was for this year's Astro Round 2.
Okay, round 2 question.
Yeah, so it's quite a long one. So I won't do every single part because some of them are just sort of plugging in numbers. But I'll go through the basic sort of theory of it. It's rather dramatically called The Fate of the Earth.
Oh, wow.
And it's basically exploring the fact that when the sun comes to the end of its main sequence, it changes dramatically in that it loses mass, but it also expands quite a lot. So I'm going to look at 3 main effects that change the Earth's orbital radius compared with the sun's radius as it expands, to essentially see what happens when the sun expands and whether it swallows the Earth at the end of the day, or whether the Earth escapes and survives.
How did you come up with this question?
Well, I just saw this article online, basically, and I read it and I thought it was really interesting. My actual question deviates quite a lot from the methods they use, because they use a lot of sort of numerical stuff, whereas I wanted it to be very algebraic and doable for sixth form students that don't have a computer on hand. So the first effect I'm going to talk about is essentially the effect of the Earth's orbital radius on just the mass of the sun changing in general. And to do this, we can use the fact that there's no external torque on the system, which means that the angular momentum is conserved. So here I'm going to assume that the Earth is orbiting the sun in a circular orbit because it's not far off. And the result holds anyway, even if it is elliptical. So we have the Earth, and it's orbiting at some speed v. And the Earth has mass little m, I'm going to say, and the Sun has mass big M. Essentially, the orbital angular momentum is going to be m, where that's the mass of the Earth, v, and then a, where a is the orbital radius. And we can write v by equating sort of gravitational potential and kinetic energy. It's quite easy to do if you'd like to do that yourself, as root g m over a, which very quickly falls into m root g m a. So now when we're thinking of what happens when the mass of the Sun changes and what happens then to the orbital radius a, we know that little m, so the mass of the planet, and the gravitational constant should hopefully stay constant, because otherwise I don't know what's happening to the universe, which means that the things we're concerned about are big M and A. And if L has to stay constant, that means that MA must be a constant. Because if this whole thing is constant, and M, little m, and G are constant, it must be the M and A that also stay constant. So M and A are constant. Now I'm going to differentiate this with respect to time. By the product rule, we get M dot A plus M A dot equals 0, and therefore we get that M dot over M equals minus A dot over A. Or, as we're basically going to be looking at A dot over A for lots of different effects, well, 3 different effects in this question, I'm going to write that as A dot over A equals minus M dot over M. The algebra will get harder than this, I promise. Yeah, so this is the effect for the changing mass of the Sun with respect to time. This is essentially the ratio of the rate of change, so it's dimensionless, which is quite nice, the rate of change of the orbital radius over the orbital radius. So this is for just the change in mass of the Sun. The next thing I'm going to look at is quite a lot more subtle. It will have a much smaller effect, but it's still an effect that we should look at if we're concerned about whether the Earth is going to live or die when the Sun expands.
We are concerned with that, I think.
Which we're concerned about, hopefully. So yeah, and that is tidal forces and sort of tidal bulges and how they interact. What tidal bulges are and how they're formed is essentially when you have a star, which I'm now going to draw as an extended object, because there it's kind of a point mass, and you have a body orbiting it. What happens is that not only does this planet experience a force from the star, obviously the star also experiences a smaller force from that object. But because this distance between them is not quite, infinite, it's a very finite distance, and because gravitational force is a function of 1 over r squared, that means that the force here at the near side of the star is going to be greater than the force at the center, which is in turn greater than the force at the edge. And what that means is that you actually get some sort of bulging in the star. It's not, obviously, you don't see the Sun as a potato, but it's very, sort of subtle. But this is essentially what happens. So now we're going to sort of calculate what's actually happening and where these forces come from mathematically. So I'm going to work out the difference between the force experienced here on the star and the force experienced here. And I'm going to say that the radius of the star is r. And then this distance here is a again. And again, this is mass little m, and this whole star has mass big M. So when we're at this point here, the gravitational force we experience is going to be Gm over A minus R all squared, pulling outwards. The force experienced at the center is Gm over just A squared. And this is the sort of difference in force experience. Okay, what I'm going to do now is I'm going to suppose that R is a lot smaller than A. So it's not really true in my diagram, but in real life, the radius of the sun is about 10 to the 8, 10 to the 9, and 1 astronomical unit, which is the orbital radius of the Earth, is about 10 to the 11. So you can kind of approximate, not quite exactly, obviously, but you can reasonably approximate R is a lot smaller than A, which means that we can get a nice, simple result for this, which means that delta F we can rewrite as GM over A squared, 1 over 1 minus R over A all squared minus 1. Using the binomial, is it binomial expansion?
Yeah.
Binomial expansion. Oh, my mind's gone blank. This is essentially 1 minus 2R over A, sorry, 1 plus 2R over A minus 1. And therefore you get, these ones cancel out, obviously, so it's going to be 2GMR over A cubed. And this is essentially, if we're talking about R being much smaller than A, it's an approximate expression for the difference between the gravitational field here and the gravitational field here. Mm-hmm. So you can see that the gravitational field here is stronger than here. So if we want to sort of work mathematically with these tidal bulges, we can't really just use them as the bulges that they actually are, because mathematically that's just really complicated. So what we're going to do is we're actually going to draw them as point masses on the surface of this star. So we're going to have the central mass in the middle, and then we're sort of imagining the radius of the star around the edge, but we're now treating the main star as a point mass. And we've now got two smaller bulges as point masses here and here, and they're going to have mass T each. Which might seem slightly horrific, but it's a good approximation to make. I promise you, it's a lot easier than working with this, so we're going to roll with it. So we want to kind of work out roughly what this tidal mass is going to be. And we've got this sort of delta acceleration here. We know that we're going to call this the tidal force on the edge. So this is the extra force / acceleration, depending on if you're working with the mass of what you're talking about. But acceleration is better because it's more general in this case. Tidal acceleration on the edge. What we're going to do is think about a sort of theoretical height of the bulges, and we're going to equate the gravitational potential energy they'd need to sort of lift that certain mass up a height off the sort of surface. And we're going to equate that with the sort of tidal potential. It's all very sort of hand-wavy, but I just want to give a general sort of justification for what I'm going to do next. We're thinking about kind of energy here, and we're saying, okay, well, we've got a bit of extra energy from this planet pulling us upwards to sort of escape the star's gravitational field a little bit. And we're going to think of that in terms of energy transfers. So the extra energy the bulge would need to go up by kind of height h from the surface would be approximately, well, it would be mgh, right, where m is the tidal bulge. And h would be like, and g would be the gravitational field strength at that point, which is equal to mt times gm over r squared. And then that times by h. Now, the potential energy that you sort of gain from this tidal force from the planet, I'm going to say is roughly equal to this times by r. Because if you think about it, if you go from gravitational acceleration to gravitational potential, you times by r, you go from 1 over r squared to 1 over r. It's quite different here. The way to actually show that this is not a completely horrible thing to do is more complicated than I'm going to go through here. But basically, trust me on this. So what we're going to say is, okay, the extra energy we need is equal to the energy we gain from that planet pulling us up. So it's going to be approximately equal to gm r squared over a cubed times by mt. Talking about energy, not potential. Okay, so what we can do now notice that I've discarded the 2 because we're working quite approximately. What we can do now is essentially rearrange to find h, because that will give us more information about what the tides are supposed to look like, and therefore sort of what their masses might be. Which means that we can get h equals, these cancel out, we get m over big M r to the 4 over a cubed. Okay, so this is essentially our height of the tides that we're expecting. Now, when we think about what this means for the mass, it kind of makes sense that it would be proportional, first of all, to the mass of the star, because it's some portion of the volume of the star, so it's going to be proportional to the mass. It also makes sense that it would be proportional to sort of the height of the bulges relative to the radius of the star. But we also need to think about an extra thing, which is the epsilon motion constant related to the love number of the planet, which is essentially a number which governs how malleable the star is to certain tidal forces, how much it stretches. The mass of the tide is approximately equal to k, I'm going to say half k because that is more conventional, times by the mass of the star, times by the height over the radius, which then works out to be half k.
Is k a constant in this case?
Sorry?
Is
Yeah,
k a
k is a
con-
constant. So k is related to the love number and to the sort of malleability of the star. R cubed all over a cubed. So this is our important equation that we've got for the mass of the tides. And we're just going to put that in a box and keep it there and sort of cast away all the weird assumptions we made just now, because they're slightly unsightly. Okay, so now we've talked about tidal bulges a lot, but what we're actually concerned about is how these tidal bulges affect the orbital radius of the Earth. And basically what happens is that the sun is not completely inelastic, which means that as the Earth moves around it, the bulges don't exactly keep up with where it is, which means it lags behind a little bit. So the Earth could be here, it's going around like that, but the bulges are still here. So there's a sort of angle distance between where the tides are aligned and where the Earth actually is. And what that means is that the Earth generates a torque on the star. The tides generate a torque on the Earth, which causes it to slow down and fall inwards, basically. And that's what we're going to work out now. Here, we've got the 2 tides here, where this is the radius of the star. So MT and MT. And then we've got the Earth somewhere here. And I'm exaggerating the angle. In reality, it's a very small angle, which we will actually use later. But we've got the Earth here. And if it's not clear, this whole thing is meant to be the sun. But yeah, we're sort of imagining it as 2 different tides and then the central mass. Okay, so this angle here, let me make that a bit thicker, is going to be called delta. And we basically want to work out what the torque is exerted on the Earth as a function of delta. So we're going to draw some lovely little triangles. So we know that this distance here is going to be A, because that's sort of the distance of the Earth from the center of the sun. We know that this is R and this is R, which means that we can then work out what's going on. We have enough information really to do all the geometry. And what I'm concerned about are these angles here. So I'm going to call this phi 2 and phi 1. The torque on the Earth is going to be, well, it's the force, the perpendicular force times the radius at which it acts. We've got 2 forces acting on the Earth that we care about. Obviously, we've got the central one going to the center of mass of the sun, but that's not going to enact a force because it's going like radially into the center of the Earth's orbit. These 2 forces, on the other hand, are not, which means that they're the ones enacting a force. So we've got F1 here and F2 here. And to find the torques, what we need is F1 sine beta 1 times by A. So that's the perpendicular force times the distance in which it acts. And I'm going to make this negative for convention. Actually, yeah, I'm going to make this negative. So this is going around like this. And then torque 2, due to force 2, is going to be plus, by convention, F2 sine theta 2 A. And now we just do a whole bunch of geometry. Tau 1 is basically equal to minus force 1, so it would be G m of the Earth mt over this distance squared. So I'm going to call this d1 over d1 squared times by sine theta 1 times by A. Okay, so now what we need to do is we need to work out d1 and we need to work out theta 1. And we can just ignore the rest of it for now. So by cosine rule, we can quickly work out d1. So the delta is opposite d1, so we can just say, okay, d1 squared equals a squared plus r squared minus, sorry, that's tiny, minus 2ar cos delta. And also we can use the sine rule in this. We can relate delta in d1 and and r in theta 1 to get sort of theta involved in the mix. So we know that d1 over sine delta is going to be equal to r over sine theta 1. Sine theta 1 equals sine delta times by r over d1. Okay, so now plugging it all in, we get tau 1 equals minus gm mt a sine theta 1. So that is sine delta r over d1, and then we've got a d1 cubed here, d1 squared here, so we'll have d1 cubed overall. But we know d1, so we can just sub this in. So we get a squared plus r squared minus 2ar cos delta to the 3 over 2. So that's T1, tau 1. Similarly, we can, I'm not going to go through it because you guys get the method, but tau 1 is going to be positive because it's going the other way. And it is nice and elegantly equal to g mta sine delta r over a squared plus r squared plus 2ar cos delta. So we can immediately see that tau 2 is going to be less than tau 1, which kind of makes sense because this distance here should be less than this distance here. I mean, more than that distance there. Okay, so what we're going to do now is some little approximations, because essentially we can again use the fact that r is a lot smaller than a. And I'm just going to do this here so I don't take up loads of space, but I'm going to factorize out a cubes, which makes this 1, it makes this r squared over a squared, and it makes this 2r over a. First of all, we can look at that and be like, nah, we don't need to bother with that because it's like a squared term of like a small thing already. So we're just going to sort of ignore this one. And then we've got another binomial expansion to do. Yay!
Yay!
Which is going to be gmta over a cubed, so we can just do a squared. Sine delta r brackets. So we've got 1 minus 2r over a to the power of minus 2 over 2. So we're going to end up with 1 plus 3r over a cos delta. And then similarly, this gets us gmta mt sine delta r over a squared 1 minus 3r over a cos delta. Cool. Okay, so now for constant torque, what we're going to do is tau 1 plus tau 2. So I'm going to squat now. Tau equals tau 1 plus tau 2, which essentially should get us 6 GMMT sine delta cos delta r squared over a cubed. Okay, now you guys should recognize this. It is the
Half angle?
double angle.
No,
Yes,
yeah.
double angle.
One of them, yeah.
So that's going to be equal to minus 3 GMMT sine 2 delta. Oh, sorry, it's really annoying with the r squareds at the end because I like to put it before the trig, but it's that way now. That's how it is.
Yeah.
Okay. And finally, I'm just going to sub in mt, which, as we got up there, is half kmr cubed over a cubed to get minus 3 g m squared k r to the 5, which is cool because you never really see like such high powers in a lot of physics. It's going to get worse than that. Over 2a to the 6. Okay, so we finally got our talk through a very long method, but it's a long question. It's supposed to take an hour, so I thought it was morally justified. So we've got the talk, but now we need to relate this to some sort of a dot over a expression, because that's what we worked with before. That's what we related the sort of m dot over m thing to, and that's what's sort of useful to find. And for this, we can say that torque is the rate of change of time of the angular momentum. So what we need to do is work with the angular momentum. And we know that L equals mRv, where v is the perpendicular, which is also equal to, sorry, this should be A, because we're still talking about orbital radius, m omega a squared. Okay, so we haven't really talked about omega at all. I don't really plan to, so what I'm going to do is eliminate that. And I'm going to do that by basically using the same thing as before, and saying that, well, we know that v equals root gm over a, and therefore omega equals v over a, and therefore omega is root gm over a cubed. So this is going to be m root gm over a cubed, a squared, which is equal to, as I realise you have already seen because I did it before, m root g big M a. Okay, and we know that this is equal to, and then we know that if we differentiate this with respect to time, we can set it equal to this, and that is correct. So L dot equals tau equals m root gm over 2 root a times by a dot by the chain rule. Cool. So we know that this is equal to minus 3 gm squared, sorry, I'm standing in front of, r to the 5 sine 2 delta over 2a to the 6. And therefore, if we rearrange to just get a dot over a, I'm just going to chuck an extra 1 over a in there so that we get a dot over a immediately. We end up with a dot over a. A dot over a equals minus 6 gm squared k r to the 5 sine 2 delta times by root a over little n, so I'm just going to get rid of the squared, root gm. So I'm just going to make this G a root, and I'm going to put a root M on the bottom. Okay, over A as well, because I added this 1 over A here. Need to remember that. And then we've also got the 2A to the 6. And collecting those all together. And also, because delta is small, what we can do is basically say sine delta or sine 2 delta is approximately equal to that argument. So I'm going to say that's approximately 2 delta, which means that we can cancel out this 2 with that 2 from the 2 delta. And we end up with minus 6 root G M K R to the 5 delta over root big M A to the 6.5. And that is our answer.
Yay.
Yes.
Amazing.
Okay, there's another thing you can plonk in here, which is essentially the eddy turnover time, which is basically a time scale used in physics that's related to the sort of viscosity kind of thing, how inelastic the stuff is in the star, so how long it takes for the star stuff to move around. And plonking that in, so the eddy turnover time, we can say is r cubed omega over gm delta, where omega is the orbital angular velocity. And therefore, we get that A dot over A is in a slightly nicer form, minus 6 km r to the 8 over T E big M A to the 8. And that is essentially because this omega has like an A to the 1.5 term in it, this r cubed comes out. So we get these slightly shocking powers of 8, which you like never see anywhere else. That's why I saw this article and I was like, that's really cool. So this is our A dot over A term. And if you compare that to sort of the big M dot over M minus big M dot over M, if we have the right numbers for the planet we're looking at, we can sort of compare these things and say, okay, would this have any effect whatsoever on like saving the Earth? Well, because it's bringing the Earth in, it will probably not save the Earth.
So this is a problem from the round 2 paper we had for the BAAO in 2024. So that's the paper, it's the second round of the Astro Olympiad, and it's a lot of people's first time doing an astro problem because you can qualify for it via the physics round 1. So we try and make these problems something that difficult physics problems that you can do without having seen all that much astro beforehand. So this particular problem, it's essentially working out how much fuel you need to send a spacecraft to Mars. And to do that, there's a whole load of orbital mechanics you need to do beforehand to work out what trajectory you're going to take to Mars, how much thrust you need to do that, and then finally you can work out how much fuel that's going to need and how much payload you can take. You can see here we've got Earth and Mars on their circular orbits around the Sun, and all we do is if we accelerate the spacecraft a bit faster than the Earth, it enters into this elliptical orbit. This is called a Hoffman transfer, and it's essentially the basis of most orbital maneuvers. I mean, you look at any space mission, and it probably boils down to a series of these with some additional complications. So the first part of the question we're going to do is we need the transfer time. So we're going to eject the spacecraft from Earth at some time t1, and then it's going round the ellipse, and it comes and it reaches Mars at its furthest point from the Sun at time t2. To get this transfer time, we need to know the period of the ellipse because we're going around half the ellipse, so we just need half the period. And whenever we need the period of an orbit, the first thing we're always going to want to do is use Kepler's third law, which tells us t squared equals 4 pi squared over gm A cubed.
This is something that would be familiar to the average A-level student taking their A-levels perhaps in a slightly different format.
Yeah, so this shows up in the gravitational fields topic on A-level. Really only for circular orbits you use it for an A-level, but it's completely true for ellipses as well. You just have to be careful with this A here. When you do it for a circular orbit, you have R, and it's just the radius of the orbit. But for an ellipse, it's A, it's called the semi-major axis, which you take the long axis of the ellipse, this one here, and it's just half of that. And this Kepler's third law is great, but there's a whole load of messy constants here, and we can't be bothered dealing with them. All the best physicists are very, very lazy. So what we're going to note now is that this Kepler's third law, it's also going to hold for the Earth. So we're going to take Kepler's third law for the Earth, and we're going to divide it. It's probably worth noting this mass here is the mass of the body being orbited. So in our case, that's always the mass of the Sun. And now,
Look
this
at that.
cancels.
Beauty.
That cancels. And we just end up with the period over the period of the Earth squared is the semi-major axis over the semi-major axis of the Earth squared. And cubed, sorry. And like we said, the semi-major axis for a circular orbit is just the radius. And we know that the radius of the Earth's orbit is 1 astronomical unit, because this is what, essentially we define the astronomical unit because it's really useful to do things like this. And then the period of the Earth's orbit, we know that, that's 1 year. So basically, you take the period in years squared and the semi-major axis in astronomical units cubed, and you don't have to worry about any of this messy junk up here. This only works for the Sun because we need the masses to cancel, so it needs to be the mass of the Sun that we're orbiting. And now we have this, then the rest is just geometry. A lot of astro is just geometry. It's what the big difference between astro problems and physics problems is the astro problems, there's more geometry going. But we can see from our ellipse that twice the semi-major axis, we can see in the ellipse that twice the semi-major axis, the distance from this closest point to the Sun to the furthest point from the Sun, is just the radius of Earth's orbit plus the radius of Mars's orbit. This symbol here is just for the Earth. It comes up a lot. T squared in years is just going to be given by this formula. We can move the 2 to the other side. Radius of the Earth, remember this is all in astronomical units, so that's 1. Radius of Mars's orbit is 1.52. We can evaluate this, and it's going to give us 1.4 years. But remember, we want in half of that, so delta T is 0.7 years. What we want next is it tells us calculate the Earth-Sun-Mars phase angle at time t1. And this is super, super important because you need to know when to launch your rocket. Because if you get this phase angle wrong and you launch your rocket, you come round here, you reach Mars's orbit, but Mars is over there, and it's a complete waste of time.
So for the pure physicists out there, what exactly is a phase angle?
Yeah, so phase angle, it's just the angle between 2 celestial bodies measured at another one.
Okay.
So in this case, we want the Earth-Sun-Mars phase angle, So that's going to be this angle phi here.
Mm-hmm.
We know that when we reach our apoapsis, so after this time delta t, we need Mars to be here, which means that this angle, this 180 degrees minus phi, needs to be the angle that Mars travels in delta t. So and Mars is on a circular orbit. That means its angular velocity is constant. So this, as a proportion of Mars's period, is going to be the same as the proportion of 360 degrees. So we just do 360 degrees times delta t. T Mars, well, we know the radius of Mars' orbit, so we just have to use this again, which is going to tell us that. We can evaluate this formula using the T Mars we can get by plugging the 1.52 astronomical units into Kepler's third law, and this is going to give us 44.1 degrees. And this is great because we know that we can look in the sky, and at the time when this angle is 44.1 degrees, we launch our spacecraft on the correct orbit, and when we get here, Mars is going to be there.
So just stepping back to see the picture, we were trying to evaluate the minimum amount of energy to reach Mars.
Yes?
Yeah.
Yeah, that's...
So now we know exactly where it's going to be.
Yeah.
Okay.
And then the next part of the question is going to take us through to find how fast we need to launch from Earth, because we've said we need to be traveling faster to the Earth to raise our apoapsis so it just touches Mars's orbit here, and we want to know how much. And to do that, whenever you need a speed on an elliptical orbit, the first thing you should think about is the vis-a-vis equation. The question wants us to calculate is the perihelion velocity of the transfer orbit, which
So for somebody like me with not much of a background in astronomy, what is perihelion velocity?
Yeah, so the perihelion is just this point where we're at the closest to the sun. You see a lot of variations of this word, so like periapsis for general orbits, perigee for an orbit around the Earth, perihelion for the sun. All of them are the same. And then apoapsis is the opposite point, so this is the furthest point from the sun, which for this transfer orbit, we want to be just at the same radius as Mars, because if we had it higher than that, we're basically wasting energy. You will sometimes see that on transfers, because if you want to go faster, then you put yourself into a higher orbit. But for this one, we don't care about how fast we get there. We just want to take the most efficient route.
So out of curiosity, is what you're going to do is find the velocity of that point and then work out the kinetic energy with which you need to launch the projectile of.
Yeah. Exactly. So this is going to be the velocity. It's going to tell us how fast we need to eject from the Earth. There's a slight complication, which is essentially the hard part of this question, which is that obviously the Earth has its gravity. So it's not just the velocity you eject from the Earth. You need to consider what's going at the Earth. But while luckily the Earth is so small compared to the sun that everything happening near the Earth, we can consider it just happening at the Earth while we're working on this scale. So we just think about ejecting from the Earth with this velocity. And then later we're going to look at the dynamics local to the Earth. And that's the velocity we reach when we're far from the Earth. So it's something that comes up a lot in astronomy because you're working in space, so you naturally get these very different scales. And that's something you can quite often take advantage of. And this isn't the sort of thing we expect you to be able to work out. The question tells you all of this. It takes you through what steps you need to use, what approximations you can make. So to get our perihelion velocity, we're going to use this equation here, which is, it's called the Vis-Viva equation. It's one of the absolute classics of astrophysics. It's one of the very few equations that you need to do these papers, which doesn't show up on A-level at all. And that's why we give it to you on the formula sheet at the front of the paper. As with any equation, apart from the ones like this where we've specifically done something different, very important, make sure everything is SI units. So this A that we already worked out, we multiplied by the length of 1 AU, which is 1.5 times 10 to the 11 meters to get the correct thing. The R is just our current distance from the sun, which is the radius of the Earth's orbit. And we can just plug all this in, and it's going to give us about 32.7 kilometers per second. So the next thing we want to do is find the velocity of the Earth, because if we're working out how fast we're ejecting from the Earth, that's just going to be the difference of the two. And you could just plug the semi-major axis of the Earth into this Viva equation formula, or you can use the normal circular orbit formula you know from gravitational fields, which is just square root of Gm over R. And we can see this reduces from this quite easily, because for a circular orbit, R and A are just the same thing. This all cancels into just 1 over R, which means we just plug in the numbers, as always, mass of the sun, and we're going to get 28.9 kilometers per second. No, 29.9, sorry. And then we need the ejection velocity from the Earth, which, because we're ejecting in the same direction as the Earth, there's no complicated vectors needing to go on here. And we can just do delta V is the per-axis velocity minus the Earth. And we can plug all this in, and we can get about 2.8 kilometers per second. Okay, so now we're going to move on to part B of the question, which is looking at what happens near the Earth. So we know we need to eject from the Earth's gravity well with this 2.8 kilometers per second. And the way we're going to do that is, if we're initially in this little circular orbit around the Earth, and it's a very similar thing to what we thought about happening before. We're going to speed up to go on a wider orbit and eject from the Earth's gravity. So we know if we speed up a little bit, we're going to get an ellipse that's higher. You probably know already, if we speed up a bit more to something called the escape velocity, then we end up on a parabolic orbit. And if we go even faster than that, then we're going to go on a hyperbolic orbit. And this is what we need to do, because if we just go at the escape velocity, then we will escape from the Earth's gravity, but it takes us a very, very long time. And when we end up far away, we're going basically at 0 speed compared to the Earth. So if we want this 2.8 kilometers per second, we need to have, once we've overcome the Earth's gravitational potential energy, we need some kinetic energy left over. So what the question asks us for is this epsilon, which is called the specific energy of the orbit, which is just energy divided by mass. And this is quite helpful because we don't know what the spacecraft's mass is at this point. We know all our formulae for energy, whether that's gravitational potential
Is it
energy
similar
or kinetic
to
energy.
the potential? It has similar units.
Yeah, no, it's the same thing. So it's just in this case, we can consider the kinetic part of the energy. So the gravitational part of this is exactly just potential, but we can include kinetic energy in this as well. But yeah, exactly, it's got those same joules per kilogram units as we see in the potential. And we know energy is kinetic energy plus potential energy. Kinetic energy is easy. That's just half mv squared, except we're dividing by m, so we'll lose the mass. What we're going to do is we're going to evaluate this essentially at infinity, so once we get very, very far from the Earth. And that's great because we know what our velocity needs to be at that point. It needs to be this 2.8 kilometers per second, so that once we zoom out again and we're looking at the wider picture we had before, we're ejecting from the Earth with that 2.8 kilometers per second. So then we need to know what the potential energy is going to be at this point. And again, that's easy because when we define gravitational potential energy, we say the potential energy at infinity is 0. And then once we plug in our 2.8 kilometers per second, this is just going to give us about 4.3 times 10 to the 8 joules per kilogram. So next thing the question asks us to do is, what is this delta V? How much do we need to accelerate from our circular parking orbit onto this hyperbolic trajectory that's going to take us away from the Earth? And the question's basically told us how we're going to need to do this. We're going to need to use energy conservation because otherwise it wouldn't have asked us to work out this energy. We know that epsilon is half v squared from the kinetic energy minus gm over r, our gravitational potential. We know epsilon, we know what r is. That's just the radius of our initial orbit here. So we can just rearrange that and get v is the square root of 2 epsilon plus gm over r. And we can just substitute in our expression for epsilon, which was just the velocity at infinity here, squared divided by 2. So it's always, when we get an expression like this, it's nice to sense check it. So what would happen if this was 0? If we wanted our velocity at 0, at infinity to be 0, and we just get square root 2 gm over r, which you might recognize as the formula for the velocity on a parabolic orbit. So this orbit that just barely escapes from the Earth without any energy left over, which is exactly what it should be. So that's reassuring that this sounds like the correct answer. And then the question didn't want the perigee velocity, it wanted the change in velocity. So we need to subtract the circular velocity. And for that, we're just going to use our normal formula, square root gm over r. And we keep working out these delta V numbers. There's a reason for that, is that basically any series of orbital maneuvers is measured in terms of delta V. Because you could measure it by how much fuel it's going to take, or how much thrust you need to apply, or the change in momentum, or any of these things. But all of those depend on the spacecraft, whereas this is true for any spacecraft. And it turns out that once you know the velocity, but once you know the spacecraft, sorry, all you need to know how much fuel it's going to take is this delta V number. Okay, and then we can just plug in all our numbers from earlier, and we get this is 3.4 kilometers per second. And again, whenever we get a number, it's always good to think, does this make sense? And in this case, it does, because if the Earth didn't have any gravity, we would just need to apply this 2.8 kilometers per second at delta V, and then we'd be on the right trajectory. But because the Earth has gravity, we need some extra 2.8. We need some extra velocity to escape from the gravity. This is all very well and good. We know how fast we need to accelerate, but the important question now is when. Exactly the same as we worked out how fast we need to eject from the Earth, we also worked out when we need to eject from the Earth. What we're going to need to do now is when in our circular orbit do we need to accelerate up to this hyperbolic trajectory, because there's no point accelerating over here, coming out on the hyperbolic trajectory and ejecting from Earth the wrong way. And this question actually takes you through quite a standard problem in this very specific context, which is we want to know essentially this angle here. You can think of this as another phase angle, but we know we want our final ejection to be in this direction, which is the direction of the Earth's orbit. So when do we need to apply the change in velocity for this line that we asymptote towards to be pointing in that direction? We're going to use angular momentum. This is something that doesn't really come up at A level, but it's a very, very important concept in wider physics. And the question tells us the formula for angular momentum, the distance from the point we're taking angular momentum around, which in this case is the center of the Earth, times v perp. And this v perp is just telling you you're taking, if you're at a certain point, then your velocity, you can break it down into the components. You have the component towards or away from the Earth, and the component perpendicular to that. And this one doesn't affect your angular momentum at all. It's only this one that you need. So for things where we're on like a circular orbit, this v perp is just the velocity. For other cases, we need to be a little bit more careful and apply some trigonometry. So the question asks us to calculate this value of h for this orbit. And because we're using the specific angular momentum rather than the version that's multiplied by mass, we can talk about the angular momentum of the orbit rather than it depending on what spacecraft is traveling on the orbit. But because it's conserved over the whole orbit and it doesn't depend on the mass of the spacecraft, talking about the angular momentum of the orbit in exactly the same way as we talk about the energy of the orbit is a very helpful thing to do. And remember we said earlier, when all our velocity is in this perpendicular direction, doing this calculation is really easy because v perp is just the velocity. And so we look for the point on the orbit where that's true, and that's this point at perigee here. So this r is just the r we've always been using, the radius of the initial circular orbit, and the v perp is just the periapsis velocity of the escape trajectory, which is this velocity we work out here. So we just have r square root 2 epsilon plus gn for r. And the question asks us to calculate this, which we can do because we know epsilon, we know all of these numbers, and we're going to get 3.34 times 10 to the 8 meters squared seconds to the minus 1. So back to our question, which is what is this angle? And this angular momentum is, as the name suggests, very closely linked to this angle because it's going to tell us how this angle changes over time. So we want the rate of change of this angle, d theta by dt. And you've seen in your circular motion topic in A level that angular velocity, which is what this is, the rate of angle with respect to time, is for a thing moving in a circle, just V over R. And in the case where we're not just moving in a circle, it's a little bit more complicated. But all we have to do is just use this perpendicular component of velocity, because that's what's telling us how the angle is changing. It doesn't matter if we're going in or out of it. That's not affecting the angle. It's just this perpendicular component. So d theta by dt is just v perp over r, which we can substitute in this formula. It's just going to be h over r squared. And the next thing we need to know is how does r change over time? And to do that, we're going to draw another diagram about the components, because we have at any time some velocity. And we can break that down into the component. This is v. We have the component v perp. So in this diagram, direction to the earth is here. So we break it down into the perpendicular component and the parallel component. And this component going along the direction to or away from the earth, this is the rate of change of r, dr dt. But we know this because we can relate it to our angular momentum. And we know this because we can just get it from energy conservation, which is going to tell us dr dt is parallel component of velocity. From Pythagoras, it's v squared minus v perp squared. V squared from energy conservation is just 2 epsilon plus P over R minus H over R squared. This V it's exactly the same formula as we used over here. In here we had it for the specific case while we're at this point, but it works everywhere. Okay, so now we want to know, how does R change with theta? Because that's what we want to know, right? Is what we write R as a function of theta, and it's going to look something like this. It's going to start at our circular orbit R, and then at some value of theta, it's going to asymptote off to infinity as we shoot out. And we want to know what that value is, because that's going to tell us this angle where we need to launch. So to do that, dr d theta, we're just going to use our normal chain rule. It's just going to be dr dt divided by d theta by dt. And we have expressions for both of these things, which is going to tell us it's dr by d theta square root. Okay, so we have this expression, and it looks quite horrendous. And in principle, this is a differential equation that we can solve. In practice, that's quite hard. There are techniques to do it, but they're kind of beyond the scope of what you're going to have to do on this kind of paper. So here we just tell you that when you integrate this differential equation up, it tells you.
I think we should challenge the viewers to derive this expression and put that in the comments.
Yes, yeah, it's a very good exercise. And this P and this E, they're just constants. And it's the angle theta here. We measure that from the periapsis. So this is theta equals 0. going, and as we move round the orbit, theta's increasing till eventually it reaches this theta we want to find, which is the one it's asymptoting towards when we look at this graph. And the P and the E, those constants, they're just expressed in terms of epsilon and H, which means that we can find the answer in terms of P and E, and that's going to give us it in terms of epsilon and H, which we've already worked out the values of. And the expressions for P and E are given in the question. So we have R as a function of theta. We need to know, when does this expression for R blow up? When do we get this asymptote? And as always, the blow up is going to happen when the denominator is 0. So we want 1 plus E cos theta is 0. So theta cos minus 1 minus 1 over E. Importantly, this E is bigger than 1, because otherwise this wouldn't have a solution. And that has a very nice physical interpretation, which is that this E tells you a lot about the shape of the orbit. It's always at least 0. So E equals 0 is a circular orbit. We can see that when E is 0, we just have R equals P. When E is between 0 and 1, we're going to get an elliptical orbit. So it's bounded because this doesn't have any solutions, so it never blows up. We never go off to infinity and escape from the Earth. Whereas if E is bigger than 1, this is going to have a solution, and so we are going to escape, and we're on this hyperbolic trajectory. Okay, so we know how to work out theta, but the question doesn't ask us for theta. The question asks us, what angle to the sun do we need to be making when we eject? And remember, we want this final trajectory to be pointing in the direction of the Earth's orbit. And since the Earth goes around the sun anti-clockwise, like we saw in the diagram at the beginning, the sun must be this way. That means that this Sun-Earth spacecraft phase angle we want is just going to be 270 degrees minus theta. 270 degrees minus theta is 270 minus arc cos minus 1 over E. E, we're given an expression for it in the question, so you can just plug your H and your epsilon into that expression. To find it, you put that into here, and this is going to give you about 113 degrees. Which is, it looks like what we have on the diagram, right? Which is always a good sign. They're not going to give you a deliberately misleading diagram. So if we can see on the diagram that this angle is somewhere between 90 and 180 degrees, it's good that we've got an answer out that's somewhere between 90 and 180 degrees. And this is really what we need to know to get to Mars, right? Because we know how fast we need to eject from the Earth and in what direction. So with this information, we really have everything we need to send a spacecraft to Mars.